Alright, we're going to conclude section 14.9 in this video. So in the last problem, we were doing 22 on page 984, 985, and I found we were given a sphere, and for that sphere we were given a parametrization, and I went through the steps to find r sub v cross the magnitude of r sub v cross r sub theta. So in the future, if you look at example 9 on page 981, they found this for you. So this is found on page 981 in example 9. For a sphere of radius A. Now that's using that particular parameterization of a sphere that's given in that problem. Now that you could parameterize a sphere in other ways, but the likelihood of us doing that is slim. So I'm pointing this out because, one, that's a lengthy process for a sphere, but the point is that if they've already done it and they did it in general for us, you don't have to do it anymore. And you've already seen me do it in an example as well. So if you need this quantity, the magnitude of r sub v cross r sub theta for a sphere of radius A, I'm not just talking in general, but this is for a sphere of radius A, they've already done it, and you can just use that. We'll see that quantity again when we get to chapter 15, so I just want to point that out now. It's found on page, and you can use that immediately. Without going through the steps again. You've seen me do it once already, and they do it in the book, so there's no need for you to do that over and over again. You just plug in whatever your radius A is. Alright, so now we're going to briefly go over one last problem. So we're on page 988, and we're going to look at number 19. So in exercises 18 through 20, find the surface area of the surface. And they give us the portion of the surface z equals xy that's inside the cylinder, x squared plus y squared equals 1. So I sent out some solutions to some problems, and I did this problem. I did it in using our favorite parameterization, x equals x, y equals y, z equals f of x, y, and set up a polar integral. So now what I'm going to do is I'm going to use a different parameterization for this, and what I'm going to do is we're going to start with our favorite parameterization, x equals x, y equals y, z equals xy. If you use that parameterization, then the textbook gives you r sub x cross the magnitude of r sub x cross r sub y. They give it to you. This is our f, so let's put that up there. It's the partial of f with respect to x squared plus the partial of f with respect to y squared plus 1. So for us, that would end up being y squared plus x squared plus 1. But we were also given our bounds where that we're supposed to be our region R. So we're supposed to be evaluating the double integral over region R of this thing. So square root of y squared plus x squared plus x squared plus 1 dA, where R is inside the cylinder. So x squared plus y squared is less than or equal to 1. So we know that if we had to evaluate this integral, we would project it down into the xy plane because we have to integrate over that region inside of there. We would get this circle of radius 1 centered at the origin, and then from that point we would convert to polar coordinates. And we are doing a polar integral in that scenario, meaning you're going to change your x's and y's in here. Your bounds are going to be 0 to 1 and 0 to 2 pi, and you're going to put a factor of r in there. So we all know that. We're very familiar with that. Now, on the other hand, there's another parameterization. I could say, okay, I'm going to ignore the integral for right now, and I'm going to even ignore this for right now. I am going to start with this. But if I start with that and I need to cover these bounds right here, what I could do is I can do a polar parameterization. There's a difference between a polar integral, which is what this is, and a polar parameterization. A polar parameterization has nothing to do with an integral, which means it doesn't dictate that we put an r in an integral if we happen to encounter one later. So a polar parameterization of this over that region, and that's the only reason I would do a polar parameterization, is because if I take this with this, I have no way of specifying what x and y vary between going from constant to constants. So instead, I'm going to do this with polar, and I'm going to let x be equal to r cosine theta. So this is an alternate approach. I will let x be equal to r cosine theta because I want to get this region. So x equals r cosine theta. I will let y right here be equal to r sine theta. And I will let z would have to be x times y. So that's just this times this. And that's r cosine theta times r sine theta. So r squared cosine theta sine theta. And now I know that I want this region. So I know to get that region, the r and theta on here, r is going to vary between 0 and 1, and theta is going to vary between 0 and 2 pi. All right, so now this is a polar parameterization. I haven't talked about an integral at all. We've done nothing with an integral. So there's no like, oh, do I add a factor of r in my integral? There is no integral right now. Now I'm going to set up an integral for this problem. And when I set up the integral for this problem, I'm doing it over this thing, which when we look at that, it would look like an actual rectangle. So if we set this integral up, or actually I'll just tell you what you're going to get. I won't go through the steps. You can go through these steps if you want to, but it's a lengthy process and you just have to be careful. So the magnitude of r sub r cross r sub theta here is going to end up being r times the square root of r squared plus 1. So you would have to take the partial of this thing with respect to r, partial with respect to theta, cross product, magnitude, simplify, you'll end up with this. So you'll get that, but now you are going to integrate this over that region. So the surface area will be the integral from 0 to 2 pi and 0 to 1 of r times the square root of r squared plus 1 dr d theta. Notice I did not tack an r on back here at the back. That r that's right there came from this. So when you do a polar parameterization, you don't tack on an r in your polar integral down in your integral down here, because it's not a polar integral. It just looks like a polar integral because we used a polar parameterization. Whereas up here, when you set this one up, so here we did it just our favorite parameterization, and it turns out that it is a polar integral. So we are going to tack on an r in here, and when we do that, you'll get an r back there. You know, this is going to get changed to r squared, and your integral will be the exact same as this integral down here. So when you do a polar parameterization, you're not doing a polar integral, so you should not tack on that factor of r in there. When you are doing a polar integral, you all already know you have you have to always put that factor R in there. So if you want to, you can go through the steps to find this to ensure that you indeed do get this. And you'll see that this is the same problem being done two different ways. If you decide to tack on an extra R in here, you're going to get the wrong integral because you'll get an integral that's different from that integral right there. All right, so we'll stop section 14.9 right there, and then in the next lesson, we'll start chapter 15.